Ladies and gentlemen, we live in a connected world. Engineering problems have long been treated in isolation. But today I hope to show you how we may be able to assess these problems in a better way, in a more holistic way, using network theory. You've been provided with a copy of this week's lecture and reading materials. This lecture will serve as a platform to deepen your understanding of those materials and give you some context and some further examples to support your learning. We will cover these materials again in tutorials and discussion groups later in the week. So as a lecture overview, what I'd like to talk to you about is networks, the different types of networks and how they work. I'd like to go through some previous examples and I'd like to leave you with a challenge. So when I mention networks to my colleagues or friends, the most common type of networks that spring to their minds are social networks. Look, I'd be really surprised to find anyone in the room that hasn't used or at least heard of one or more of these social media platforms that are listed here on this slide here. There's Facebook, Twitter, Tumblr, Pinterest, Flickr, LinkedIn, YouTube, there's many others. Fundamentally what they do is they provide a network through which people are able to connect. They keep in touch and they are updated with the people that they know and or care about. And they are huge. As of January 2015, Facebook alone had more than 1.15 billion users per month. To put that in context, this is about 3 times that of all of Google, which had about 350 million users per month. This is an important fact. To understand why networks are so useful, we must first have a clear understanding of the incredible scale and absolute pervasiveness of networks within today's society. Now, while there's been substantial changes to the level of connectedness within my lifetime, I could only imagine that this will be a fraction of what happens in the years to come, and why it's important for you guys to understand this. To my mind, networks are one of the most scalable and powerful tools we have available. To date, the uptake of engineering analysis using network theory has been modest. It is in my opinion that there is a significant potential for growth in the use of these theories for the solution of problems within all fields and areas of engineering. There are 2 types of networks that we'll be discussing today: social networks and conventional networks. So social networks focus more on the interrelationships between people and groups, but on large scales. And conventional networks, which are similar, have a greater mathematical basis and bias and can be applied to any problems. They're more generic. Let's have a look at each type more closely. Social network theory originated in the 1930s with a small group of German psychologists. They studied how an individual related to others within their social group depending on the individual's psychological state at any given time. By far their greatest contribution to the area was in the development of a sociogram, which is shown here. It's a diagrammatic representation of a social network. People are identified as the blue dots or nodes, and the relationship between those people are identified as the lines or links. So later in the 1950s, the concepts outlined in the social network theory were joined with a branch of mathematics known as graph theory to produce what we commonly now know as the conventional network theory. So an easy way of remembering it might be that conventional networks are essentially social networks which are underpinned by maths, and that type of math is called graph theory. Now, to understand how and why networks actually work, it's important for us to get a feeling for some of the key characteristics and the behaviours of the networks. These can best be explained by describing the 6 degrees of separation, the theory of weak ties, and the emergence of scaling and hubs within these networks. So I'm sure you've all heard of the 6 degrees of separation. This is the basic idea that every person in the world is related to each other in 6 or less steps. Now, there's been quite a bit of research done in this area by different researchers starting from the 1929 right through to current days. A lot of that research was put on the back burner until the 1990s, when it was again popularised by, of all things, an American college drinking game. In this drinking game, a lot of actors and actresses would try to be linked back to Kevin Bacon using Bacon numbers. So Bacon numbers are essentially the degrees of separation. I've got a link here which in your own time you might be able to go in, and what it does is you can link all the actresses and actors back to Kevin Bacon, and you can investigate their own Bacon numbers or degrees of separation, and you should be able to do that through time with any actor or actresses with Kevin Bacon. Now, the theory of weak ties was an idea that was brought into play in early 1970s, 1973, by a guy named Granovetter. And he did his research into job networks and how people actually got their jobs. And what he found was that the majority of jobs were found and sourced not by what people knew or through the processes of recruitment, but who they knew. So he came up with a theory of weak ties. And weak ties can be categorised as providing a bridge between two otherwise remote or unconnected networks. They are essential to network performance, and they provide linkages across these networks which shortcut the serial pathways which would otherwise need to be taken. This was developed on by more researchers in the late 1990s, and they published a paper called Collective Dynamics of Small Worlds. Now on the next slide we'll go in and I'll explain that with a bit of an example. So the theory of weak ties might be best explained using this diagram. So we move from structured networks on the left through to unstructured networks on the right. And it might be best or easiest if we think of this like trying to communicate around a football stadium. So all the little red dots are people sitting around a football stadium. In the olden days where there was no mobile phones, no interconnectedness between people, you would have to pass the message from one person around to the next person, to the next person, to the next person, much like Chinese whispers. And so you'd have a long link of interconnected people all the way around, but there was no shortcutting the system. So that's basically the diagram on the left. Now, as technology is improved, we've got mobile phones, so you might know somebody that sits across from you, or a few people down from where you're trying to get to. So you might be able to ring the mobile phone, and you can take those shortcuts straight across the stadium. So you might only have 5 or 6 links to go to, or steps to get the message from one side to the other. Now, with further advances in technology and things like Tinder and the like, you can get pretty much anybody in a circular radius from you, and there's a whole lot of interconnectivity which goes on there. So that's shortened the amount of links that you have to step to get from one person to the next as well. So it's a higher level of interconnectedness which comes through the random networks and these weak ties that you've got. Now, the single most important development in network theory was conducted in 1999 by a guy named Barabasi and his research assistant Raka, where what he found was there was 27 examples of networks that he found at random which exhibited mathematically similar traits, and what he did is he tracked and he placed and he traced these networks over the top of each other, and he found that they all behaved the same way. And that was with the spread of diseases, sexual contacts, different movie actors, social networks, and overt or light networks, so like military stuff. The American military versus Al-Qaeda or ISIS, or whichever we want to do, so the development of different networks and how the structures affect their behaviour, which is particularly interesting. The most important part to come out of that was the identification of hubs. Now, what we've assumed until now is that basically all nodes had the same amount of connectivity. This is clearly not right. What we can see in this picture here is the number of nodes, and there's some highly connected nodes here, and that's what we call hubs. So we can look at this picture here, and what we can see is there's some highly connected nodes in America, or lots of them. You know, like we've got Chicago and Atlanta on the east coast, and New York on the east coast, and LAX on the west coast. Over in Europe, if we have a look at that, we can see all the densification of the things over there, all the flights in there, and we've got Charles de Gaulle and Heathrow there, and Beijing are obviously hubs in this context. Network theory is incredibly powerful and has the potential to be considered in a wide variety of engineering problems, regardless of whether the application is civil, electronic, computing, mechanical or chemical. Now, we live in an increasingly hyper-connected world. My challenge to you would be this: Now that you know a little about network theory, explore it further. Consider it during degree and after you've finished in practice. And report back. Let me know what you find. The truth is out there.